The Indus River carries roughly 180 million acre-feet of water every year down from the Himalayas and into the plains of Pakistan. For most of recorded history, that water simply moved through, flooding farmland in summer, leaving it cracked and dry by winter. In 1968, engineers began closing off a gorge near the town of Tarbela, in what was then one of the most ambitious civil engineering projects ever attempted in Asia. What they built there is, by volume, the largest dam on Earth. It holds back a reservoir roughly 80 kilometers long. It protects millions of people downstream from catastrophic seasonal floods. And it is made, in its overwhelming majority, of dirt. Not reinforced concrete. Not interlocked stone blocks. Not a monolithic arch of poured cement. Dirt. Compacted rock and clay, piled into a structure containing roughly 121 million cubic meters of material, enough to bury Manhattan under more than 150 meters of fill. The finished embankment stands roughly 143 meters above the original riverbed. If you have never thought hard about dams before, your instinct is probably the same one most people carry: the bigger the water pressure, the harder the wall has to be. A concrete dam, a masonry dam, something solid and rigid and unyielding. The idea that the world's largest dam by volume is essentially a shaped hill of earth should feel like a mistake. It should feel like building a firewall out of paper. It is not a mistake. And by the end of this, you will understand not just why it works, but why, for certain conditions and scales, it works better than concrete could. The false belief worth naming explicitly is this: that a dam's job is to stop water completely. Engineers do not actually try to stop water entirely. They try to control the energy of water as it moves. That distinction is everything. Start with the physics of pressure. When Tarbela's reservoir is full, the water behind the dam sits at a height of roughly 472 meters above sea level. The dam crest sits at roughly 485 meters. The riverbed below the dam sits about 342 meters above sea level. That means the water at the deepest point of the dam's upstream face is under pressure equivalent to a column of water more than 130 meters tall pressing outward and downward. That is roughly 13 atmospheres of hydrostatic pressure at the base, the kind of pressure that will find every crack, every void, every weak seam in any structure. Concrete resists that pressure rigidly. A concrete gravity dam works by being so massive and so strong in compression that the water simply cannot push it over. That works. Hoover Dam on the Colorado River is a concrete arch gravity structure. Its curved face transfers the water's load laterally into the canyon walls. It contains roughly 3.3 million cubic meters of concrete. Itaipu on the Parana River between Brazil and Paraguay uses a series of concrete buttresses and hollow sections totaling roughly 12.3 million cubic meters of concrete. But concrete has a limit. Rigid structures crack. When a concrete dam develops a crack, from seismic movement, from thermal expansion, from the slow settlement of its foundations, pressurized water enters that crack and the physics turn hostile. Water under pressure in a narrow crack acts as a wedge. It does not just leak through. It actively forces the crack wider. Engineers call this hydraulic fracturing, and it is one of the ways concrete dams have failed catastrophically. Rigidity, in the presence of a flaw, becomes a liability. An earth-filled embankment does something entirely different. It does not try to stand rigid against the pressure. It tries to make the water forget it was ever under pressure in the first place. Here is the actual trick, and it is one you can explain to anyone in a sentence. The dam forces seepage water to travel such a long, tortuous path through carefully graded materials that by the time any water reaches the downstream side, its pressure has dropped to almost nothing. Think of it this way. If you drag your heel slowly across a gravel path, you lose speed gradually, smoothly, controllably. If you run full speed into a concrete wall, you stop immediately and violently. Tarbela is the gravel path. It bleeds the water's energy away over distance. The way this is achieved is through what engineers call a zoned embankment. Tarbela is not simply a pile of random fill. It is built in carefully designed zones, each one serving a specific hydraulic function, moving from the upstream face to the downstream face in a sequence that is almost biological in its logic. At the core of the dam, running vertically through its center, is a zone of compacted clay. This is the primary barrier. Clay particles are fine enough that water moves through them extraordinarily slowly. The permeability of the clay core is measured in fractions of a millimeter per year of flow. The clay zone is roughly 21 meters wide at its crest and widens significantly toward the base, where the pressure is highest and the contact with the foundation matters most. Immediately on either side of the clay core are filter zones, layers of sand and fine gravel, graded carefully by particle size. These filters serve a critical and counterintuitive purpose. They do not stop water. They catch clay particles that might otherwise be carried by seeping water out of the core. If clay particles migrate, a process engineers call internal erosion or piping, the core gradually hollows out from the inside. The filters are graded so that their pore spaces are large enough to let water pass freely but small enough to trap and hold the clay fines. They are a net fine enough to catch the smallest particles while allowing the water itself to move. Outside the filter zones are transition zones of coarser gravel and crushed rock, and finally the outer shells of the dam, large rock fill and random fill material that gives the structure its sheer mass and stability. The whole thing is like a layered composite material, each layer optimized for a different part of the same problem. Now here is something that stops most people cold when they first hear it. Tarbella leaks. By design, it leaks. Seepage through the embankment and foundation is not a sign of failure at Tarbella, it is a sign that the system is working exactly as intended. Engineers monitor that seepage constantly. A network of instruments and drainage galleries underneath the dam collects and measures the water that passes through. As long as the flow rate stays within expected parameters and the water emerging is clear, not carrying clay fines, not discolored with suspended particles, the dam is healthy. The moment seepage water becomes cloudy, that means particles are moving, and that is the warning sign. Which of these systems would unsettle you most to be responsible for? A rigid structure that has held perfectly for decades but gives no warning before a crack propagates, or a structure that is always quietly leaking but tells you exactly how it is behaving? Tell me in the comments. The history behind this matters. Tarbella's construction, completed roughly in 1976 after years of work by a consortium of international contractors, was not without problems. Early in its operational life, the spillway tunnels suffered severe cavitation damage, where the high-velocity water flowing through the tunnels caused vapor bubbles to collapse against the concrete lining with enough energy to physically erode the surface. Sections of the tunnel lining were destroyed. Engineers repaired the damage and modified the tunnel geometry over subsequent years. That episode is a reminder that even a brilliantly conceived structure meets real-world hydraulics in ways that no model can fully predict. But the embankment itself, the zoned fill, the filters, the clay core, has performed as designed for decades, managing seepage from a reservoir that, at full pool, contains roughly 13.7 cubic kilometers of water. For context, that is enough water to cover the entire land area of England to a depth of roughly 10 centimeters. What Tarbella represents, beyond its raw scale, is a philosophy of engineering that runs counter to how most people think about strength. True structural resilience is not always about being the hardest, most unyielding thing in the system. Sometimes it is about being the most controlled, the most layered, the most deliberately permeable. The dam does not fight the water. It tires the water out. It gives the pressure nowhere to concentrate, no single point to attack, no crack to exploit. The energy dissipates the way sound dissipates, gradually, across a vast and forgiving medium. There are roughly 800 large earth-fill and rock-fill dams operating around the world, storing water for agriculture, flood control and power generation. Most people who live downstream from them have no idea what is inside them, no idea that beneath the grassy slope and the riprap facing, there is a precisely engineered sequence of materials, each one doing a specific job, each one monitored constantly, each one part of a machine that works by letting go rather than by holding on. We are surrounded